Okay, welcome everyone to this final CDAC webinar of 2021. Today we're pleased that Professor Maosheng Miao from Cal State Northridge has agreed to give a second talk of this calendar year. Maosheng is a theorist focusing on the fascinating problems of structure and bonding in materials up to very high pressures and has been quite prolific in the last few years. Previously, he gave a talk on novel chemistry under pressure, highlighting a review article he wrote with some colleagues, including Eva Zurich from CDAC, that was published in Nature Reviews. And today, Maosheng is going to focus on how to understand, really in a chemical sense, the complex structures that emerge in so-called simple elements or metals, elemental metals that emerge at very high compressions. And this builds on earlier work he did with Roald Hoffmann. This is also a topic of interest to our group and many others in the field. So as I mentioned previously, Maosheng received his bachelor's and PhD in chemistry from Jilin University. And after several postdocs, he moved to Cal State Northridge in 2013, where he's now Associate Professor of Chemistry. So over to you, Maosheng.
Okay, okay, wonderful. Well, thanks. Well, first I definitely like to thank Russ and the CDAC to give me this opportunity. I kind of feel that I get, free rides from a big, airline company. Okay, and also we recently have done this work on very simple, very focused topic on very simple metals, the structures, and we find that it's very interesting, and we like to hear some opinions and comments. And we know that in this audience we have many people has very great experience and background on this topic. Okay, so here's a little outlines. So basically, I want to introduce the problem first about the metal structures. And we believe that it's a problem that hasn't been solved, although many people may think that it has been solved. But it is truly a very long time puzzle for us. And then we try to propose a new view for metals. So instead of thinking of metals as like free electrons, we need to really emphasize the actual localizations in the metals. And then we will show how to use this new view to explain three different kinds of structure preferences. First is among the closed packed structures, some metals prefer FCC, some metals prefer HCP, and that can change under pressure. And also, the second is, I think is the most important, is why there are so many metals take BCC structures, which is not closed packed. There are some reasons that people understand previously, but I will show you from our point of view, there's a very unique reason hidden behind the electronic structure of the metals. And then, of course, the most interesting for us is the high pressure structure evolution. For us, this high pressure thing is not only that, if you have a theory about metal, you need about metal structure, you need to be able to explain the structure evolution of metals under pressure. So that is a requirement. And also, it uniquely shows us how does the actual localization change or evolve in a very systematic way while you change the lattice, and how correspondingly the metal structure will change because of that. And at the end, it's a little discussion in the conclusion. Okay, so talking about the metal structures, the most simple structures are the BCC, a body-centered cubic, and the two most common closed pack structures. Some metals take a little more complicated closed pack structures with different stacking orders, right? But most of them take just FCC and HCP, right? Only if the energy of these two structures get really close, then of course some other stacking, more complicated stacking structure may appear. Okay, but if we look at the metal structure, the pattern of the metal structures across the periodic table, immediately we notice some, a lot of puzzles here, right? So first, for example, all the alkali metals, they basically adopt BCC. Well, lithium is probably an exception, and we'll show that, there's a reason behind that. Lithium depends on the temperature, right? So I think the room temperature, it takes FCC. Whatever. So the alkali metals, they adopt BCC. And if you look at the alkaline metals, the top four, they adopt closed pack structure. And even among the closed pack structures, the beryllium and the magnesium, they take HCP structure, and calcium and strontium, they take FCC structure. However, the beryllium, suddenly, it behaves more like alkali metals and take BCC. So that's very puzzling. So apparently the number of electrons doesn't totally determine the structure the metal can take. And if you look at the transition metals, it's also very puzzling. If you forget about this exceptions BCC structures here, there's a general trend. The early transition metals tends to take HCP structure, but late transition metals tends to take FCC structure. Except then suddenly, while you move to zinc and cadmium, which can hardly be considered a transition metal anymore, but they suddenly take HCP structure. And if you look at HCP structure, there's also some puzzles in there. For the early transition metals of beryllium or magnesium, the COA ratio is not ideal. It's slightly smaller than the ideal value. However, if you look at zinc and cadmium, the COA ratio is not smaller. It becomes much larger. And I'm going to show those values are exceedingly larger than the ideal one. So what causes all this, right? And just to add more complexity, suddenly the group 5 and 6 transition metals take BCC structure instead of the closed pack structures, right? So there's definitely some puzzles here, for us to understand with simple theory, hopefully. And while we put pressure on it, the puzzle, we get more puzzles, right? So for example, the alkali metals, under ambient condition, they are BCC, that's stable in BCC structure. But while you apply pressure, most of them will convert or transform into FCC structure. And if you keep increasing the pressure, all these simple structures becomes unstable. And then the system will start to adopt some complicated structures with open sides and also with low symmetry. And that's another thing that puzzle is very puzzling. We have some understanding on that, but not in a systematic way. So why these good metals, very active metals, exemplar metal elements under higher enough pressure, they abandon the closed pack structure, they abandon the simple structure, and then they start to take the complicated structures. And if you look at the alkaline metals, that's also very interesting. They all start with the closed pack structures, HCP or FCC, but once you compress them, they start to become BCC. Remember, the BCC are the stable structures of alkali metals, and they are not closed packed. And then if you further compress them, and then again, they all abandon the simple and high symmetry structure, and they become, structures with open sides, the structures with low symmetry. Right, so that's the alkali. Okay, so these are the puzzles that we summarize here, and here are the general view that we need to change in order to understand them. But the conventional metal bonds is based on a simple structure, based on a simple view, is that the electrons are detached from all the atoms, and then they freely moved in the metal lattice, right? And that's the concept of electron C, and each individual electron state is like a free electron or near free electron gas, and it's shared by all the the ions, and the metal bonds are this metal ions bonded by these electrons that are freely moving inside the electron, the metal lattice, right? So this is what we call the delocalized picture of an electron of metal bond, right? And based on that, of course, we try to use this picture to understand the structure pattern of the metals and also their changes under pressure. And there are, a bunch of theories out there, right? So, for example, a rigid band. So if you look at the DOS, for example, for metal elements across one period, then they look pretty similar, except the number of the electrons are different, and then you feel them. You feel this density of states. You feel this bands up to a different level. And then for particular metals, for example, group 5 and group 6, for BCC structure, it goes into a big dip in the DOS. For example, that is one possible theory, right? And there's another theory, is this very delicate Fermi surface nesting, right? And that particularly used to explain why we compress the metal structures changes, and eventually they abandon the simple metal structures, right? And there are several others. For example, this very famous Pettiford pair potential. So this theory is a kind of has several problems. Is that the first thing is not any theory can explain all the phenomena, right? And also very often the theory is basically our description of the DFT results, right? It's not truly a mechanism that hidden behind all this that you can understand with our mind, that is the driving force, that drives the structure pattern and the structure change. Very recently, actually a very successful one is this dynamic instability, because it can apply to many metals. It works, and there's a recent. I'm sorry that I didn't list that. There's even a review article on Review of Modern Physics. And you can see it's a very long review article. It lists almost all the metals, transition metals included, and their behavior under pressure. And they all show for most of them, why you have our phase transition, especially while the BCC structure or the XCC structure becomes unstable. They are also at the same time become dynamically unstable. So that was proposed as a reason. However, if you think it deeper, the dynamic instability itself is a phenomena. It's not a reason. So what causes this dynamic instability? And actually, with all this progress, our puzzle, our conundrum is not smaller, it becomes bigger. Now we are adding a new problem. The problem is why, for this metal structure changes, it's always accompanied by our dynamic instability. Right, so that is another question that we need to answer. All right, so here is the overview. And overview, and as Russ said, really originated from the work that we have done some time ago, with Rode on high pressure electride. All right, so let me briefly. I'm pretty sure that most of you are very familiar with the topic. But just briefly go through that. So, it has been long notified or noticed the phenomena is many metals under high, enough pressure, it may become insulating or, semiconducting, has a smaller gap. Okay, and a very famous example is this sodium under 200 GPa was predicted first by theory, and then was confirmed by the experiments that were published in the same paper by Yanming's group. So the sodium under 200 GPa suddenly becomes an insulator with a gap. The DFT gap is about 1.4 EV, right? And then the DFT calculations show clearly the reason. The reason is simple. From the DFT theory, the electrons start, the sodium suddenly takes a structure that has an open sides, and this large, empty sides can accommodate the electron, and two electrons will occupy one side, and it plays the role as an anion, like a sulfur and oxygen takes two electrons. So therefore, the sodium becomes an insulator because it's as if it becomes a compound, right? The sodium 2 sulfur, for example. It actually takes exactly the same structure as sodium sulfide under, I think, 16 GPa or something, right? And the theory that we propose is that really the open site can be represented by a local quantum orbital. And this local quantum orbital can start to take electron, especially its energy will changes with pressure. And the energy level of this quantum orbital, or quasi, what we call the quasi-atom orbital, relative to the atomic orbital, will change under compression. So under higher and higher pressure, because the atom has core electrons, it repels the valence electrons. So therefore, you don't have much room to accommodate that electron here. So therefore, the atomic orbital energy increases much faster than the quasi-atom orbital because you don't have a core here, right? So this is just a simple view. You can say that there's an equivalent, it's just an equivalent view, right? But I will show you that this equivalent view has power because it's simple and you can apply it to understand many complicated phenomena then. Okay, so and then under certain pressure, and this energy, this orbital energy becomes lower, and therefore start to accommodate electron, as if that you have an anion here, right? So that is the reason that it drives the sodium becomes electrolyte under high pressure. So here's one advantage of using this simple picture. For example, the lithium case is actually more complicated, right? If you do a DFT calculation, the lithium electride was first discovered by experiments, and for quite a while, people don't even know its structure. And there's a lot of crystal structure search work, and it was about the same time. You know, the people in China and people in Britain, find this structure. But while you calculate the electronic structure with DFT, you find something very positive, because it also has open sites. But in some of these open sites, if you calculate the number of electrons occupying there, you will find it's better interpreted as singly occupied. Those states. If you have a singly occupied states, that means it should be a metal. However, lithium electride is not a metal. It has a small gap of, I think 0.3 eV, much smaller than sodium. So what's behind that? Well, from the quasi-atom point of view, it's pretty easier to understand, is because if you observe those two singly occupied quasi-atoms are very close to each other, and their distance are among, I think, 1.3 or 1.4 angstrom, and they form strong chemical bond. We can even identify the wave function of the bonding states, and also another one is the anti-bonding states, very clearly show that. And therefore, the gap in this particular electride is actually the energy difference, or the energy gap between the bonding state of and anti-bonding state of this chemical bond formed between the quasi-atoms, right? So this is an easier view, to apply this concept. Well, before we apply this view to metals in general, let me just show something in the tools that we use. The tools we use is called electron localization function. Well, there's some math formula behind that and some reasoning behind that. I only want to emphasize one thing: electron localized function that does reveal the quantum nature of electrons. Especially, it shows you the occupation of the orbitals. So this is the major difference between electron localization function and just density. Okay, so for example, if you look at ELF for an atom xenon, if you look at density is higher is at the center and then goes down, goes all the way down. But if you look at ELF, you can clearly see the shell structure. It shows you the occupation of the orbitals peak at the different radius, right? So that's, and also if you look at ELS for a molecule, you can clearly see the occupation of other quantum orbitals, for example, the lone pairs, and also the bonding states, the covalent bonds, that the occupation of the molecular orbital between these atoms. So you can see that, and also the electrons. That's also very clearly show that the electrons. If you see the ELF, you can see that the electrons occupying this local orbitals or the quasi-atom orbitals. Okay, so how if that we apply this to metal structure at low pressure or at ambient condition, just 0 GPa or one atmosphere, right? For DFT calculation, one atmosphere is 0 GPa for us. Okay, so well, not true, but we usually don't see that small differences. Anyhow, so let's say for sodium, the 0 GPa structure is body-centered cubic, right? And for sodium at 80 GPa, the most stable structure is the face-centered cubic, the FCC structure. If you calculate the ELF, you can see a ELF pattern like this for BCC at 0 GPa, and ELF pattern like this for FCC at 80 GPa. So you can see that ELF has maximum localized at the deformed tetrahedral center of a BCC structure. Right, so here's a tetrahedral. You have 2 sodium here. You have 1 sodium here, and you have 1 sodium up in the front. Right, so you have 4 sodiums. So here, this is the center of that tetrahedron. It's deformed. It's not perfect. And the maximum is right at here. Right, is right at here. If you look at the density is very, very uniform. However, if you really tune it very carefully and signify the difference between the maximum point and neighboring points, you do see that it shows a little maximum, although the value between this point and this point is very, very small. It's very, very uniformly distributed. But if you simplify that, you can see that there's indeed a maximum here. And if you do a subtraction of the density of the whole lattice, subtract the individual atom densities, then you can clearly see the maximum here. That means the electrons will flow into here. If you start from the single atom density for each sodium, and then you let it go in the same lattice, and then the electron will flow into this region, in other words, will occupying this state, which we also can assume it as a quasi-atom orbital. And you can see also clearly the wave function, the crystal orbital. And then you take the gamma point, and then you can see a particular wave function. This one is the one that closest to the Fermi level, but it's an occupied orbital. And you can see that this one has also a maximum at this tetrahedral centers, so showing that the electron occupying the states, right? It's even clearer for FCC. So if you look at FCC at 80 GPa, then apparently it has maximum at this octahedral site. It also has some small, to smaller amount. The value is smaller. The maximum value is smaller. The volume is also smaller. But it also has. It shows the maximum at the tetrahedral center, right? So you have both octahedral center and tetrahedral center, but mainly for sodium FCC is at the octahedral center. And we will see that it's not true. It really depends on the metal you're talking about, and especially depends on the lattice parameter. So while you change the lattice parameter, you're going to change the electron localization at the different sites, and that really determine eventually the structure evolution. And again, if you carefully tune the density, you can see that the density show a slight maximum at here. It is a maximum, but the value difference is very small. And if you look at the density difference, you can see clearly that the electron flow into this area while you combine them and form a real lattice. And then also you can identify the wave function showing the occupation of these quasi-atom orbitals. So this means, that if you see the differences between, this ELF and the wave functions with the the sodium high electron electride, high pressure electride. The difference is there, the quasi-atom orbitals are fully occupied. So this quasi-atom orbital are fully occupied. It takes 2 electrons. Therefore, it's electride. It's just like oxide or sulfide, chloride, right? So of course, that valence orbital are fully occupied, right? So that is what. But if you look at this, they are not fully occupied. They are partially occupied. And if you calculate the values is not very small. It's 1/4 or 1/2 of what we can see from the the electride. So the occupation is not so small. However, it's partially occupied, and of course it is partially occupied because it's metal, right? So so instead of viewing this as an electride, it's not an electride, but we can call it as, if we use the parallel name, electron corresponds to electride, then this one should be called, electron compounds. So it's basically formed by the metal atoms and quasi-atoms, and quasi-atoms plays the role of, the negatively charged atoms, right? So maybe you have some p block, atoms, or you form some intermetallic compounds. So some metals play the role of, occupying or accommodating electrons and negatively charged, and therefore, so this should be called. So the simple metals are not really simple metals. They're actually can be viewed as compounds, right? So this is the thing that we will propose. Okay, so one more thing to prepare to understand. The other thing is this electron localization is a very general phenomenon. It doesn't really matter whether you have a stable metal, whether you have metal corresponds to a structure under particular pressure. If you have a lattice, it's not a stable lattice for this metal. It doesn't matter. That is one thing. And second thing, the localization of these electrons really evolves while you change the lattice, right? So for example, the simple one, if you take a simple cubic, and we have a good reason to say why we take simple cubic lattice. Okay, so let's say we take simple cubic lattice of sodium, and we start at our parameter of 0 GPa, but this 0 GPa is actually the BCC sodium lattice constant at 0 GPa. So basically we take BCC sodium and we remove the atom at the center, and then we have this simple cubic lattice, which has the same lattice parameter as the BCC sodium. And if you calculate that, you can see that the electron localized, very much localized at the bond center. However, it also has a large value at the phase center, right? So if you compare those two values, is this one and this one, and this one, and the value in between is here, right? But if you compress that, then the general trend is the electron localization. If you compress your lattice, the electron localization at a larger lattice constant, it always localized at our position that has less neighboring atoms, right? So for example, it occupies at a larger lattice constant, it occupies here, it localized here, and it has only 2 neighboring sodium atoms. But while you compress that, it will move, that maximum will move to the phase center, which has 4 neighboring atoms, neighboring sodium atoms. And if you further compress that, it will eventually move to the body center, which has 8 sodium atoms, neighboring sodium atoms, right? And another very interesting feature is why you compress this from this length, further down here, the electron maximum actually moves, and you can see that it's very fun to see it. The maximum actually shifts for sodium, not for all the atoms, but for alkali atoms, alkaline atoms, they all show this feature. It shifts from the body center, from the bond center, or from the edge center to the phase center. And at a particular point, of course, for sodium is exactly at 5 GPa. this localization, this high risk electron localization point will locate at the midpoint between the edge center and the phase center. And that is a very important point. Just remember that we'll come back to this because it's very important to understand some structure changes. Okay, so now we can apply this new view to explain the metal structures. So let's start with the simple one, the closed packed structures. Well, the FCC versus HCP, and as I said, the metals. There are three sets of puzzles. One is the alkaline metals. So why beryllium and the magnesium take HCP, and calcium and strontium take FCC. Okay. Another puzzle is why early transition metal take HCP, and also why their COV ratio is smaller than 1.633, which is the ideal ratio for an HCP. Also, it is also true for beryllium and magnesium. And the third puzzle is why zinc and cadmium take HCP. However, their COV ratio is much larger than the ideal value, right? For zinc is 1.856, and cadmium is 1.885. It's huge. It's much larger, right? So for this, they're smaller, but they are 1.62 or 61 or something, right? I think there in some extreme cases like beryllium is 1.58 or close to 1.6. Okay. If you look at the differences between the FCC and HCP structure, right? They're both close packed. They're both close packed. So they're both close packed, and for each atom they all have 12 neighbors. So they are not the differences of topologically. The overall differences is there. However, the local environment is very similar for the two. However, if you look at the interstitial sites, and if you see their local environment, they are very different. So here is the tetrahedral interstitial of HCP and FCC, and you can see the tetrahedral interstitial in FCC. They form a perfect simple cubic lattice. Okay, so these are the diamond structure, the occupation, right? The quarter, right? And you have eight of these interstitial sites in one lattice, in one FCC unit, right? Conventional unit, and they form a simple cubic lattice. However, if you look at HCP, they form pairs. So the two tetrahedral sites, they form a pair. So you can imagine that if you have electron localization here, then the localized electron at this quasi-atom orbital, they will strongly interact. And that's exactly what happened for beryllium and magnesium. So if you take beryllium, because of the particular lattice length and that, remember that this localization changes with the lattice, but because of the particular beryllium local lattice there, the electron mostly localized at the tetrahedral site. They do have small occupation values at the octahedral site. It's also maximum, but that value is much smaller than the occupation of the tetrahedral site. For comparison, the calcium is totally different story. The 0 GPa calcium, if you calculate the FCC structure, then it localized mostly at the octahedral sites. And for the HCP structure, also it occupies the octahedral sites. For beryllium, the electron localization will happen mostly at the tetrahedral site, for both FCC structure and HCP structure. But of course, because HCP structure, the tetrahedral quasi-atom, they form pairs. So therefore, they, if you calculate the electron localization, they actually form a very strong chemical bond, and therefore, they stabilize the HCP structure and also reduce the COV ratio because of this strong chemical bond here. Okay. On the other hand, the calcium does not have that feature, and actually the localization of electrons at the octahedral site stabilize the FCC, because the FCC has a larger Madelung constant, right? If you view this as ions, positively and negatively charged ions, then the Madelung energy is lower, for FCC structure. So that's for alkali metals. For transition metals, you see the similar feature. So forget about the body center. Let's just compare the HCP and FCC structure. Then we can see that for early transition metals, you have a large occupation at the tetrahedral site. So therefore, you have a stronger bond between these two quasi atoms. Therefore, it stabilize the HCP structure. And the general trend is that the electron localization becomes lower and lower for both octahedral and tetrahedral sites, right? So eventually, the localization at this sites are not determining factor for the structures, and the transition metals in that case prefers the FCC in general, except at the end, group 12, that's zinc and cadmium, you can see a large increase of the the ELF at the tetrahedral sites, so indicating that for zinc and cadmium, they have a large electron localization on those sites, and therefore it has a higher chemical interaction there. However, we still don't understand why COV ratio are actually higher there. Well, here is why. So instead of comparing this with alkali metals and early transition metals, the electron localization not only happens at this tetrahedral size, but also happens at this triangle size. So basically, the electron for zinc and cadmium in this lattice, with this particular lattice length, the electron can also localize, at the center of 3 zinc atoms. Okay, remember that the general trend of electron localization. If you have a larger lattice, then it always tends to localize in between 2 atoms. But once you decrease that, it starts to move to the size that has more neighboring atoms, right? So it shifts from 2 to 4 to 6 to 8. And for HCP, zinc and cadmium, it actually also has a very strong electron localization at a site that has 3 zinc and cadmium neighbors. And because of that, this site has also very strong interaction with the electron localized at the tetrahedral sites. And they form, in total, they have a very strong interactions there, but then they have very weak interaction between the different stacking layers. So therefore, if you view this as a compound, it actually is a layered compound. Okay, so it formed a layered structure. The interaction between the layers are pretty weak. So therefore, the COV ratio is exceedingly large. It's very, very large. Okay, so this is a story of the FCC, the close packed structures. So now the stability of BCC structure. So this is special. So the way that we understand that is metals should always take the most closed, the close packed structures, right? Always take that. It's only for some particular reason. There's a driving force, drives the metal to take BCC. Okay, and here is, the driving force. How to understand? How to dig that driving force out, right? So so why BCC can be stable at all, and why certain metals are in BCC structures? So these are the 2 questions. So in order to understand, we should think of the metal lattices in this way. So metal lattices can be split into 2 subsets. There's of course numerous ways of splitting them, But the most effective way of revealing this interaction is to split them into two equivalent subsets, right? And we can do that for both FCC structure. You can separate them into two equivalent subsets, or HCP structure, you can split it into two equivalent subsets. Especially for BCC structure, that's even more straightforward. It's very easy to split that into two subsets because it basically forms by two simple cubic lattices, right? It's just an intercalation or interpenetration of the two simple cubic lattice. And also it's comparing with FCC and HCP, the split of the BCC lattice is perfect in the sense that every atom in one subset has only the atoms from other subset as neighbors in the original BCC. So for example, this atom, it belongs to this sublattice, but its nearest neighbors are all from the atoms of another sublattice or subsets. We tend to use the word subsets because sublattice seems to have a very special meaning. So that is one thing. So in that sense, BCC is indeed special comparing with FCC and HCP. For FCC and HCP, you can never find this perfect split. That is one thing. And another thing which is very important is the high symmetry position of the two subsets. They have particular relations. So for example, a phase center of one subset is the edge center of another subset, right? And another important point is the body center of one subset is the atomic position of another subset, right? And also a very important feature is this midpoint between the edge center and the phase center. This point is the same for both sublattices. That means if it is a midpoint for one sublattice, it's also the midpoint of another sublattice, right? So this is the very important geometry feature for BCC, BCC lattice. Okay, so here is one possible cases why we put two simple lattice together to form a BCC lattice. Okay, so let's say we take sodium BCC at 5 GPa as an example. Okay, and if you calculate the ELF, the electron localization happens at this tetrahedral sites, the maximum, right? So if we assume this whole lattice, both yellow and black balls are the BCC lattice atoms, right? And then you have the localization happens at this sites, and assuming that these sites are the tetrahedral center, right, or the tetrahedral sites, they form the tetrahedral sites, right? Now, if you split this into two sublattices, you split them, and then you recalculate the electron localization. You have many possibilities. But for sodium BCC at 5 GPa, if you calculate just for one single cubic, which is a subset of the whole BCC lattice, you find the electron localization falls into an exact same pattern as the original BCC. So now you have electron localization at exact same location as the overall BCC. Okay, and the same, of course, is also true for the other subset. And remember the midpoint. This is the midpoint. The midpoint for the two subsets are exactly the same points. So this means if you interpenetrate these two simple cubic lattice together, these two electron localization will match each other exactly. They will help each other, they will like each other, and therefore they stabilize the BCC structure. And we do have our perturbation theory but it's very simple and very straightforward. It's just basically put it in the math formula for the word that I'm using. Okay, so that means the electron localization of this lattice will help the stability of the electron localization of this lattice and vice versa. And therefore, they help each other and they stabilize the BCC structure. So this is what we call the subset matching mechanism. And for sodium BCC at 5 GPa, it's at the perfect matching point. On the other hand, if you compress the sodium BCC, if you compress it up to 70 GPa, if you calculate the ELF for BCC, it doesn't change much, right? The localization maximum are still at the tetrahedral site. However, if you calculate the electron localization of the subset of the simple cubic, now it's totally different. The electron localization moves. Remember, it tends to move to a size. While you shrink the lattice, it tends to move to the side that has more neighboring atoms. So if you compress it to 7 GPa, then it moves to body center site. Okay, and the body center site is exactly the location of the atoms of another subset. So suddenly you are facing a very different scenario. So now your electron localization of one subset is exactly on top of the atoms of another subset. And you can imagine that the subset has core electrons and it repels electrons of that, right? They don't like each other. So therefore they work against each other, and we call this a subset repulsion effect. So just a simple summarization, and we have a simple summary, sorry. We have matching case, we have mismatching case, which is a little more complicated. And then we have repulsive interactions case, right? So there are several different types of subset interactions. It could be more complicated, but those subtle differences, it's hard for us to judge. I don't like complicated factors. So fortunately, the matching and the repulsion can explain most of the cases, right? The complications, if you add all the factors, complications all together, it becomes so complicated, then why not just go to do density functional calculation, right? The first principle calculation. Okay, so here is the thing. So let's say the alkali and alkaline earth metals. For alkali metals, it is very clear. So this shows the ratio between the value of the ELF at the midpoint and the value at the edge center. So for alkali metals, they are all very close to 1. And in some cases, for example, cesium, the maximum point actually is already at the midpoint. So that means cesium at 0 GPa is already at the perfect matching, subset matching point. And for others, well, for lithium, it's also very close. However, lithium has complexities, and I will show you. And that is why all these points are getting close together. That's because lithium not only has matching, but at the same time, it also has repulsive interaction. It also has very large electron localization in the body center. So lithium case is more complicated than the other cases. And for the other alkali metals, even if they are not at the perfect matching point, they're very close. If you just compress them a little bit, you shift to the matching point. For example, potassium, if you compress it to 0.7 GPa, you will shift it to a perfect subset matching point. So therefore, alkali metals are stable in BCC structure under 0 GPa. And if you look at the alkaline metals, they are much farther, especially for early alkaline metals, much farther from the matching point, and there's some other reason, because their FCC point are actually closer to the matching point. FCC and HCP are closer to the matching point. But again, as I said, the BCC split is perfect. So if both are at matching point, it's always BCC wins, because the BCC interaction, remember the BCC split is perfect. Every single atom does not have the neighboring atoms in the same subsets, right? So that's really the geometry. It's not even the chemistry, it's the geometry matters. The only exception for alkaline metals is beryllium. The beryllium at 0 GPa, it is already at the perfect matching point. Okay, so therefore the beryllium is the only one, although it has the same valence configuration, right, as all the alkaline metals, But because of this electron localization difference, beryllium take the same structure as alkali metals and take BCC. Transition metals, the same story, except it's slightly complicated. We need to invoke, several matters. But the reason that the group 5 and group 6 taken BCC is still that it's close to the matching point. Okay, but for the early transition metals, why they don't is because they have very large, repulsive effect. So the body center, the ELF at the body center is also very large, but quickly gets down for the group 5 and group 6, and that really is the general trend. So all the ELF localization goes down for transition metals while you have more and more d electrons. However, the body center goes down much faster, and the phase center and the midpoint, goes down much slower. So therefore, it reaches the matching point, and there's no large repulsion for group 5 and group 6. Okay, so these are the transition metals. So metals under pressure. Okay, I just very quickly go through that. I mean, with all those previous understanding, it's very straightforward to understand what happened under high pressure. So you started with, for example, let's take sodium as an example. At 0 GPa, it's not at the perfect matching point, but it's very close. So therefore, it takes BCC structure. But if you compress it, then it will shift to phase center, and then eventually the body center, and becomes the subset repulsive interaction, right? But at the same time, while you have very strong subset repulsion for BCC, the FCC does not have that strong subset repulsion. However, if you increase the pressure to 110 GPa, even FCC, you can see very clearly the electron localization. So this ELF values that's shown here are calculated by the subsets that's shown by this yellow balls, right? And these white balls are the other subsets, and they locate exactly at the maximum of the ELF. That means it locate exactly at the electron localization point of the other subset. So therefore, they have very strong subset repulsion. So that explains that. And it also explains the dynamic instability, because the reason that all this high symmetry structure becomes dynamic unstable is because the two sublattices or two subsets, they're repulsing each other. If you move the atoms away from that, you lowers the energy, right? From that particular point, you lowers the energy. So therefore, if you calculate the phonon, your phonon will have negative mode or imaginary mode, right? So imaginary frequency, right? So that's the overall reason, right? It's very simple. And the similar story happens to calcium, except the calcium is a little far away from the perfect matching point for the BCC. So therefore, it starts with FCC structure. But if you compress it, then it becomes subset matching for BCC. So therefore, BCC becomes stable. Remember, if all the lattices are subset matching, then BCC always win because the split is perfect. And then if you increase the pressure, the BCC again becomes unstable, because it develops very strong subset repulsion, right? So that's the same story. And then let me skip these two things. It's just with our theory, you can more easily explain what happened here. So another thing is why all the high symmetry structures become unstable under high enough pressure for this metal. And the reason, of course, again, is the repulsion, the subset repulsion. So for example, let's take sodium as an example. Under high enough pressure, like 100, 110, it becomes this structure. And this structure is actually can be viewed, it's a deformed BCC, right? So you can actually still split it the same way as a BCC structure into two deformed simple cubic structure. And you can calculate the electron localization in the same way as BCC, right? If you calculate that for the two subsets, then you can find the electron localization maximum is here, is actually shift away from the exact location of the atom from another subset. So this is the driving force. The system want to avoid this repulsion, this subset repulsion. And if you calculate the distance between these two is fairly large. For 110 or 100, around 100 is almost 0.5 angstrom, right? So it's fairly large shift away from the other subset. So therefore, that is the driving force for the lattice to take more complicated structures. So we have some other, further work, but that's not, for this topic and for here. I will skip this. So it's basically, it shows all the structures can be viewed as a compound, right? So this structure can be viewed as a compound if you view the occupation of the electron at the quasi-atoms, then it's isoelectral to this beryllium arsenide. And for this particular structure, you have two different kinds of quasi-atoms. And if you view that, then it's equivalent to this compound, right? And of course, this typical, famous example, and it's equivalent to this compound, right? Okay, aluminum, I will skip that. It has a complete story, but I think I can. So let me just make the conclusion. The chemistry inside metals. So we need to change the traditional view. The physics view. It's not sufficient to understand the structures, but instead we viewed it as a complex chemical system, and it's not just the change of the view, because it does. Can explain that and tells you the real driving force in a very simple manner, right? And we show that this can be explained, the three different topics, the three different structure trends. Okay, so this is a change of the view. So the electron in metals, of course, is homogeneously distributed, right? If you calculate the density, unless you go to very close to a nucleus. But here the density are very homogeneous. However, homogeneous, distributed can be done in two different ways. One is that every single electron, are delocalized everywhere, and and then it creates the homogeneity, right? Another way is you patch this electron together. The electron occupies locally at different quantum orbitals. You patch them together, and you still have a homogeneous distribution, right? So that's the new view. Okay, so here's the acknowledgement. The team, Yuan Hui is a postdoc working with me right now. He did most of the calculation. Lei Zhao, he worked with me for a couple of years. And now he's back to China. The whole topic starts from while she was here. And Yun Hao, he's a professor in China. And collaborators, I really had a lot of discussion with these people in the past and for this topic. Rod, Russ, Chris, while I get these results, those are the people that I'm thinking to discuss with and send them the results and have discussions with them. Ram is a professor here. He's a very good chemist, and he really likes the idea. Also, Walter is a physicist, and he also likes very much the idea. He knows about a lot about the band structure. He's from really from the point of view of the physics, of the band structure and so on, band feeding, those point of view. But he's very happy to see all this phenomena can be explained here. Okay, so the fundings, the career award from NSF, MRI, ZEED. We don't use much ZEED right now, but we use that a lot in the past. It says PRF, and this is CSUN, the place that I work. I showed it here not because that I'm working here, but also they do give some small money. So everybody give money or can be converted to money are listed here. Okay, thank you. I'm very sorry that I might take too long. It's almost an hour. It's basically an hour, but hopefully I can have a little time to answer some questions. Thank you very much.
Yes, thank you, Maosheng, for an exceedingly interesting talk. I'm sure there'll be questions. So questions, comments, just
Can I jump in, Russ?
Yeah, go ahead, Anand.
So yeah, absolutely great talk, and I'll speed it up because we're short on time. But one of the questions I have is when you talk about pressure in terms of theory, you're talking about uniform compression, the hydrostatic compression. As experimentalists, when we do experiments, we obviously see non-hydrostatic stresses and so forth. And as a result, we have seen intermediate phases, right? Example is titanium, zirconium. You get this, intermediate omega phase between the HCP to BCC transition. In lanthanides, we see it gets more complex because the F electrons. But point being is, can you comment why are some metals more willing to adapt this intermediate phases, and then some metals you can share them, it changes the formation mechanisms, but doesn't change the structural phase transitions?
Yeah, okay. Well, thanks. It's a very nice question. Yes, indeed, it is some complications, of course. Many of this complication comes from the kinetic point of view. So what we are doing here is more thermodynamic. We compare the energy difference between different structures, and of course everything is not only confirmed. So this is good about doing research on an old topic, is everything has been confirmed over and over. So all these structure difference preferences has been observed by the experiments, and also most of them has been reproduced by DFT calculation. Although DFT calculation have complexities in there. A lot of complexity in experiments, of course, that's the reason that the experiments are always hard to do. And many of them are indeed not only from the thermodynamic stability, but also from the kinetic point of view, especially while you have this non-hydrostatic pressure situation, right? So the transition from one state to the other state, you might need to go through an intermediate states, and very often, for materials is even more clear, because while you don't have pressure, your phase transition, in my opinion, is even more complicated. It goes through, the shift of the stacking fault, the move of the dislocations, the kink, and all those motions. So eventually, which state that you arrive at is really complicated. And if you have a complicated situation like a non-hydrostatic pressure, then you add more, possibilities. Yeah, absolutely.
And it becomes, I guess I was alluding to, it becomes even more complex these days as we, push for this, advanced manufactured materials where you intentionally introduce lattice strains, and I was just trying to get to, where can we expect, these
absolutely. And I think eventually, so right now we're trying to keep, looking at simple things because it can signify the theory. Eventually, I believe this theory can be applied in many places, in phase transitions, in the grain boundary, in dislocation, all those places. I'm pretty sure this electron localization will play a very important role. But we are at very, very early stage for that.
Thank you.
So one comment. Several years ago, we looked at the role of symmetry here. You described the traditional view as a sea of electrons, a Fermi sea, but if you actually look at where the electrons are, then you have a different space group representation of the structure. So there's subgroups, supergroup relations that also help you look at these kinds of transitions that you're idealizing.
Yes, that was a great work.
This is what Ivan Novak did, yes.
Yeah. No. Yeah, you're talking about a PRL paper you published with Ivan Novak.
Yeah, he's on the Zoom call. Mm-hmm.
Oh yeah. Yeah, that's very good. Actually, that is indeed related, because if you look at the FCC sodium, the symmetry restricted to be or metal, and in our point of view, it's restricted in a way that the quasi-atom orbitals can only be partially occupied, and only while you transform to to another structure under 200 GPa, then the symmetry. I call it the unlock of the restriction, and then you can occupy two electrons and become insulator.
Hey, Roel has a question.
Yes, that's a great talk, Maosheng.
Thanks.
Very interesting new view of how to look at metals. I have one general comment just with respect to the community and one specific about references. I guess I take a reaction from the beginning to anyone who says that BCC is low coordination, because that's a view in terms of nearest neighbors and touching spheres, which ignores the next nearest neighbors, which may not be far away. I think that a productive way to think about BCC is 8+6 coordination. And if you then take the 6 and calibrate them by some exponential fall off of the distance that might give you a measure of the interaction, you will come right back up to the neighborhood of 12, which FCC and HCP. So I think your theory is good, but don't make BCC look bad in the context of coordination. It isn't. This is, and this goes really for our teaching about it. I think in terms of references, I wanted to mention just that I think everyone knows the moments work of which uses the method of Cyril-Lachmann, which Pettifor and Burdett especially have used to analyze the energy differences. And that is another way. The HCP FCC differences is very slight. It occurs only in a fifth moment of the distribution. But I wanted to mention, and I've mentioned it to you, but other people may not know it. There is a Spanish crystallographer, Angel Vegas, who did not know much about electronic structure, but was extremely knowledgeable about structures. And he had this idea that the electron density at the interstices in some metal structure was the place where you would get electron density if there happened to be electrides or that would form compounds. And Vegas has written a book, which I would recommend to people to read, called Structural Models of Inorganic Crystals, which is a rare book, but it's out there and it's very interesting. Great work.
Okay, thanks, Rod. Thanks a lot. Well, indeed, no comments about BCC. I think you're absolutely right. I mean, it's very close packed. But if you look at the filling factor, it's still smaller than FCC and HCP. I mean, the difference is very subtle. However, if you consider the energy difference between them are also very subtle. Actually, we have struggled with, getting the energy orders correct by doing DFT calculations. And this is why we observed something very interesting, very weird. Very often, the straightforward ELF analysis will match this experiment much better than the DFT calculation if you don't do a DFT calculation very, very carefully, going to very, very high K points and choosing, various of exchange correlation function. But anyhow, I think the BCC story, from the chemist's point of view, it shows this driving force, right? That stabilizes it. But that's okay. And another thing, just to add one more fact about the BCC. So following your suggestion and don't look down the BCC, I just learned that from Chris Picard. So he mentioned that actually, if you take a uniform electron background, uniform charge background, and then with the positive point charges, then if you just calculate the modern energy, then the BCC actually is the most stable one. So that's another story. Yeah, but you know, with this story, with the subset matching and subset mismatching and repulsion, you can not only you can explain that BCC becomes stable, and eventually also you explain it becomes non-stable, right? So that's I think it does reveal something really hidden there. It's the driving force. Anyhow, talking about the WIGO, thanks for that. Well, I actually got his book. He published a lot of paper, and it's very hard to find them, and because those journals are not in the in our library and UC library. But anyhow, so I got a book which is indeed very good. I think his work is more related to our other work, which we are trying to put together and also publish. We have our manuscript. I can send you the manuscript later. So that's how to use the electron localization of a metal lattice to understand the compound, the stability of the compound, the structure of a compound. That's related to this topic. However, for this particular topic, I think the key is that you understand the localization. You understand them is not just a high value of ELF, but also is the occupation of a local atomic orbital. And therefore, because of that, they can have very strong chemical interaction between them, and so on. So I'm still reading the book, and hopefully I can relate that more to our work at a later time. In the new version, I do cite this book.
So that also suggests another way of looking at the Humer-Rothery rules for compound formation in solid solutions. But Jorge Monez has a question.
Yes, hello. That was a really amazing talk. It crystallized a lot of thoughts. Yeah, no pun intended.
Thank you. Thanks so much.
So coming from a physics point of view, I started with band structures, and then I started integrated the electronic density of states, and then thinking more about the orbitals. So I have been studying equiatomic iron vanadium and iron titanium. And so I think the closest that I got to what you're doing is with the asphericity. So just dividing, the charge in the T2G electrons and the EG electrons. So I was wondering if you can say something about magnetism, and perhaps about having different. I guess you have the two cubic lattices if they are made out of different atoms.
Yeah, of course. Thanks. This is what I understand a theory. It starts with something simple, and hopefully it can explain everything. But of course, all theory, not any theory can explain everything. There's always complications. And in those complications, it has complications because there's few more factors will chip in, and you need to consider them. Magnetism is definitely one. So in transition metal structures, for example, I avoid talking anything about magnesium or iron, and I think it's there probably the spin or the split of the d orbitals can play more role. But what really encourages us is that this theory works very nicely for simple metals, the S block metals, and even for D metals. Although with the different number of D electrons, the D splitting, the spin interaction should contribute a lot. But it works, surprisingly well by just not considering them for most of the cases. But of course, there are definitely some cases, as I mentioned, magnesium and iron probably. You cannot avoid neglecting those factors. And in some intermetallic compounds and alloys, I'm pretty sure that those interactions will become important. And for example, for some other metals, for example, the polonium, I think is that the way they'll call it. It has a very unique structure, and I think, I mean, it does not against our theory, but our theory has no way to explain it, and it's a simple cubic structure. It's the only one. I think Rode definitely knows that. So it's the only example that a simple metal takes the simple cubic structure, and there's no way for us to explain that. And I think it's probably because of the relativistic effect or spin orbit interaction, for example, plays an essential role in there, and that is really goes beyond the simple theory can cover. Yeah.
Thank you.
Thanks. Yeah, thanks.
Sabri Elatrash has a question.
Yes, indeed, a very interesting topic and talk. Thank you. My question is about the repulsion force in BCC. Whether do you have seen any sign of the repulsion force in the liquid state, and whether this one, like a repulsion force, will make the material adapt new structures similar to BCC, not only as the pressure increase, but only maybe at the temperature increase.
Yes, yes. It's very relevant. Thank you for asking this question. And again, as I said, while you have a theory, you start with something simple, but of course, with the hope that the theory can apply to many other places. And I definitely think the melting, this localized election will definitely play a very important role in the melting. I mean, if you have this repulsive interaction, then of course you will destabilize your structure, right? And then of course it encourages to melt in some sense. And the melting, of course, is more complicated because in the liquid state you have a time-dependent interstitial structure now, right? So it's not like crystal that everything is fixed, right? And then you can discuss, in a very easy way of this. But in the liquid states, it's very different. But that only means that you need to use some other method to study it. But it definitely has and the temperature effect is definitely true, because in some sense you can kind of mimic that effect by expanding your lattice. And while we do that, we can see. So, for example, in the case of lithium, you can see the change of the electron localization does toward to the experimental observation. So in the sense of stabilizing, I think FCC is zero at 0 degrees or stable. I think on the higher temperatures BCC. So it's definitely fits that. But we didn't invoke that. Again, it's some complication in there. So we want to keep it simple and also work in simple cases. But this is definitely relevant. It's definitely relevant. And I'm pretty sure, this picture will also be important in understanding high temperature and melting phenomena. Thank you. Thanks. Yeah.
Thank you.
Okay, thank you. Are there more questions? If not, thank you, Maosheng, for not one, but 2 great talks this year.
Okay, thanks. Well, thanks for giving me the chance. And as I said, a free ride.
Thank you.
Okay, happy holidays, everybody.
Okay.
We'll see you next year.
Okay.
Thank you. Bye.
Bye. Bye.